Good morning once again, everybody. Thank you all for coming. The goal for today is to discuss some questions that are still unsolved in the field of fair division. Uh, and whether you are a master's or a PhD student looking for some problems to work on or just want to try fair division for fun, these might be some of the questions that you might find interesting. So just a small sample of a few questions. This is going to be a very short session. So if you have any open problems to suggest yourself, please feel free to do that. But here are some of my favorites. And once again, we are going to make the division between divisible and indivisible. So let me start by a few problems in cake cutting. So the first one is about the query complexity of NV freeness. So remember that we saw some algorithms for computing NV-free divisions in certain special settings. For example, when you have only two players, we have the I cut, you choose algorithm. And that required only two queries in the Robertson Webb model. For the case of three players, we saw another algorithm called the Selfridge-Conway. And I gave it out as an exercise problem to tell me the number of queries, and I remember one of you did, and he has rightly earned himself a cold coffee. Others did not. So, so this is again a very small number of queries, and that's pretty much it. As far as a small number of queries go, these are the only nice cases that we have. For n bigger than equal to 4, for general number of agents, we have the Aziz-McKenzie protocol. Whose worst case bound is, like we said, like we saw that there was quite huge. Okay. Maybe for n equals to 4, it's slightly better, but for general number of agents, it's really huge. And the trouble is that there is the lower bound that is known for this problem is much smaller than this. So a lower bound is by Procaccia. It's a lower bound. This is Nichkai 09 paper. And it is n squared. Okay, so any algorithm for computing NV-free divisions requires these many queries in the worst case and at most these many queries. There's a huge gap here, and the question is very simple: close the gap. Clearly there's a huge gap in our understanding of uh, the best and the worst scenarios for computing NV-free divisions. So it would be really great if we can sort of narrow down this gap. Okay, that's like the broad research agenda here. Let me point out a few more specific questions. So one could start by thinking about special classes of valuation functions instead of working with the complete general beast. One can work with special classes of valuations and try to get improved bounds in that case. And there are some results already known on those lines. So one is uh, so when the value density function, the thing that we drew that day, the So when the value density function is a polynomial of degree d, then it is known that you have an order n squared d algorithm. So that's the number of queries. D is the degree of the polynomial. In particular, for low degree polynomials, this is an interesting result. Okay. So this is due to Brunze from 2015. That's a special class of valuations for which we have a nice bound. There's another result for something called a piecewise linear valuation function. So piecewise, okay, so people remember what piecewise uniform and piecewise constant valuations were? So there were these chunks of the interval where the valuation function was either the same, had the same height, or maybe had different heights, but it was a constant height within each interval. Piecewise linear gives you somewhat more of freedom. The valuation function can be linear within each part. Okay, so the picture is like this. Say this is the cake. Maybe it's 0 here, and then goes up here, goes down again, maybe 0 again, something like this. Okay, and for this case, it's known that NV-free allocations can be computed in order n to the 6 k natural log of k queries. Here k is the number of breakpoints. Okay, so these jumps, how many jumps are there for each agent's valuation? That's what k is capturing here. Okay. And this result is due to Kurokawa et al. From the AAAI 14 paper. So in certain special settings, as you can observe, we have better bounds, and it would be nice to have similar bounds for other interesting classes of valuations. That would really help us understand where does the difficulty lie in coming up with these bounds, right? What are the necessary assumptions on valuations, which ones are not, and stuff of that nature. Okay. Another thread that one could pursue in this agenda is exploring the power of simple algorithms. So this algorithm is quite sophisticated. It involves a lot of different things, and they have to be put together in a clever way to make this algorithm work. Whereas these two algorithms are much simpler. Okay, especially cut and choose. It is so easy to describe. Even self-rich Conway, it's somewhat non-trivial, but it's still a simple algorithm. Whereas this algorithm is far more sophisticated. So it would be nice to have an understanding of how well do simple algorithms do, even in special cases of this problem. Okay, so here's what I mean by this. So there's a recent result for the case of n equals to 4. This is a very new result. It's from SAGT of this year. So the authors have or I should say they have improved the query complexity for this specific case of 4 agents uh, from about 600, which was how many queries the Aziz-Mackenzie protocol needed, to less than 200. This is a very specific, very special case. So this is the Aziz-Mackenzie protocol. But the message here is that for special cases of the problem, perhaps one can come up with simpler algorithms and even get better query bound. Okay. So the reason the bound here is so large is because it's dealing with a general number of agents, but maybe for a smaller number of agents, we can make certain additional assumptions and get query bound and even arguably simpler algorithms. So that's another thing that one could think about. Okay. For example, what happens for 5 agents? Can we do better than the Aziz-Mackenzie protocol, perhaps with a simple algorithm, right? So that's what I had to say on this topic. There's a closely related topic of approximate EF with connectedness constraints. So if everyone was awake yesterday, we saw an algorithm for computing an approximate NV-free allocation with connectedness constraints, right? I presented the proof only for 3 agents, but it generalizes easily to any number of agents. Now, what is the query complexity of that algorithm? How many questions does the algorithm need to ask the players? Recall that the questions were in the form of which piece do you like the best for this cut, right? And the answers were essentially the labels of the triangulation, right? Whenever we got an answer, we labeled one of the vertices of the triangulation. And you can imagine that for a fine enough triangulation, you might need to ask a lot of questions. In fact, there are results which say that in the worst case, you might need an exponential number of queries. I think it's n minus 2 or something. So n is the number of agents. Epsilon is how fine your triangulation is. I'm not defining it formally. Feel free to go ahead and read the specific definitions. What I want to convey is that you in the worst case you might need a lot of queries, exponential in n many queries. This is I think a result by Deng et al. It's an operations research 2012 paper. Okay. But maybe by making certain assumptions on the valuations, we can get away with a smaller number. Okay. So the question here would be, for what classes of valuations does so I'm calling the algorithm that we saw yesterday the path following algorithm, where we walk through the doors through the house. Let's call it the path following algorithm. Yeah. So for what classes of valuations, for what structured inputs does that algorithm require, say, a polynomial in n number of queries? Okay. And here is a starting point. So here is a useful assumption that one could make. on the valuations, and this is the monotonicity assumption. And we've already seen this. So this means, say I have a, so again, think about three agents. Say there is a cut of the cake with lengths x1, x2, and x3. Okay. And say one of the agents, say agent A likes x1 at this cut configuration. Okay. Now it is reasonable to expect that for any cut where x1 becomes bigger and both x2 and x3 become shorter, that agent's preference will still be piece 1, right? The piece that you like the most is getting bigger, and any other piece is only becoming smaller. It is reasonable to expect that you continue to like the piece that you originally liked, the biggest piece, according to your valuation. So in the picture that we drew yesterday, this is what it might mean. So this means that piece 1 is the entire cake. This means that piece 3 is the entire cake. And suppose here, say this point is 0.5, 0, 0.5. So in terms of the cake, this looks like, this is piece 1, piece 2 is like length 0, and piece 3 is 0.5. Okay, so that's this point here. If some agent likes at this point piece 1, then for all of these points here, it better like piece 1 as well, right? In other words, if that agent tells you that its label is 1 here, you can just fill in the labels for all of these points. You don't have to ask about these labels any longer, right? And that's a handy assumption, because by asking a few questions in this triangle, we can chop away a large territory of it. We don't have to ask questions about like some non-trivial fraction of the area of this triangle. So now the question is, can we do this formally? Can we actually obtain polynomial query bounds using this idea? Okay. So this paper has something on those lines for the case of 3 agents, but for general number of agents, I think this problem is still open. So definitely worth thinking about. Questions? Yeah. Well, if the valuations are easy, then there are different algorithms that work. But my specific interest is in making the algorithm from yesterday also work. So I want to prove something about yesterday's algorithm when the valuations are nice and easy. So that part I don't know. And it would be really useful to understand whether yesterday's algorithm has nice running time guarantee or nice query complexity guarantees. Sort of an implicit reason why I'm asking that question is because Sperner's lemma is not useful only for cake cutting. It shows up in all sorts of places like game theory, in Nash equilibria. So if we have a good understanding of under what preferences this path following algorithm uh, has a nice running time, maybe we can say something about other settings as well. So it's just a good way of understanding when these things are efficient. Any other questions? Okay, so here's my third and final open question in the cake cutting world. There are many others, but these are just the ones that I've cherry picked. And it's about something that I think someone asked me in the first lecture. What happens when uh, the valuations are negative? So maybe you dislike some part of the cake. It's also known as a mixed cake. So remember that when we defined the valuation functions, we made the non-negativity assumption that maybe they are induced by non-negative value density functions, which are basically probability density functions. Uh, but that need not always be the case. Maybe we can relax that. So maybe your valuation for the cake looks something like this. Okay, so this is the positive part, this is the negative part. Maybe you strictly dislike this part of the cake. Okay. Now the trouble with such valuations is that a strictly bigger piece is not necessarily a better piece, right? So monotonicity goes out of the window. And because of that, many of the algorithms that we have seen will no longer work. So a concrete example is the Selfridge-Conway algorithm, where we used the idea of trimmings to talk about this irrevocable advantage, right? We said that even if the other agent gets all the trimmings, the cutter is not going to envy that agent, right? That was conditioned on the assumption that there's a monotonicity happening, right? Uh, such things are, you cannot make such arguments any longer with these mixed valuations. So so you need to come up with different arguments. And actually, there are very few results known in this, partly because this is a very, very recent problem. So here's what is known about this problem. Okay, so first of all, exercise. For the case of two agents, check that cut and choose still gives you an entry allocation. Okay. So for two agents, this problem is still solvable easily. The interesting bits are for three or more agents. So for n equals to 3, it is known that a connected EF allocation exists. Okay, this is a result due to Sigal Halevi from this year's AMAS. This is the paper that actually that formalized this problem. A very nice paper. I encourage you to read this. Uh, so it gave an existence result only for this n equals to 3 case. And soon after this paper, there was a generalization for n equals to, so when the number of agents is either 4 or it is a prime number. Okay, and you can have a similar result. So like this extension is due to Monnier and Zervi from, it's a paper on arXiv. So that's all that we know about this problem in terms of existence results, right? And so the questions are, I think, pretty obvious here. Fill in the existence results and also think about the computational results. I think this is a very nice problem to sort of make some progress on. Very, very new and very interesting. Interestingly, this paper requires a generalization of Sperner's lemma. So this is because it's something that we've already seen. Uh, Maybe it might be easier to read up. For n equals to? That's a great question. So although they, this paper shows existence using a variant of Sperner's lemma, turns out that you can no longer use that path following argument to prove the existence of the fully labeled triangle. So there are other techniques to do it. So I don't know of any algorithm for n equals to 3, but maybe there is. I just don't know. That's a good question. Yeah. For unconnectedness, I'm not sure. Maybe there is. I'm not sure. I think so. This paper has certain suggestions on what algorithms might work when you don't have the connectedness requirement, but I don't remember seeing a theorem that you can always find it or some such thing. So I'll check and let you know. All right. So this is all I had to say about cake cutting. Let's move to indivisible goods now. And the first question in the indivisible goods category is one that I really like because I was fortunate enough to be involved in that result. Uh, so the question is about something that we saw yesterday, the Nash social welfare objective. Remember that we saw this theorem which says that a Nash optimal allocation is EF1 and PO. EF1 is N51 good, PO is Pareto optimality. And we saw another result which says that maximizing the Nash objective is NP hard. Okay. So if you care about these two properties together, perhaps computing a Nash optimal is not a great idea because it's a hard problem. Okay. But that does not mean that computing an allocation which is both EF1 and PO is also hard. Right? It's just a one-way implication. So that leaves the question whether we can compute EF1 and PO allocation in polynomial time via algorithms, right? And turns out you can. So, well, sort of. There is a pseudo polynomial time algorithm for computing an EF1 plus PO allocation. So do people understand what pseudo polynomial time means? Anyone who doesn't? Okay. So, think about what the input instance to the fair division problem is. It is simply the number of agents n, number of goods little m, and the valuation matrix. Yes? The valuation matrix is composed of these numbers Vij's. Now, a pseudo polynomial time algorithm simply means that the running time of the algorithm depends not only on how many things are there in input, but how big they are, the numbers Vij's themselves. Okay, so this running time is basically a polynomial in n, m, and Vij's. It depends on the value itself. Okay, so it's actually, you can think of it as the maximum utility. It depends on the max utility, but I'll just leave it at that. Note that if all the valuations have a constant cap, say all the Vij's are less than, I don't know, 10, okay, then this algorithm is honest to goodness polynomial time. Okay, if all the Vij's are small, bounded by a constant, then the running time is simply a polynomial in n and m, because this just gets filtered out as a constant. Okay. So for bounded valuations, uh, the algorithm is polynomial time. And the reason I'm pointing this out is because computing a Nash optimal allocation, i.e. maximizing the Nash objective, continues to be an NP-hard problem even when the valuations are all bounded by a constant. Okay. So what this result is saying in particular for the bounded valuations is that while computing a Nash optimal is sufficient to get EF1 and PO, it is certainly not necessary, assuming P is not equal to NP. Okay, so this is result with my advisor and another student. This is from this year's EC. Now there's this annoying pseudo polynomial time in sitting there in the theorem statement, and that's the one that I want to get rid of. Okay. So the question is, either come up with the polynomial time algorithm for finding an EF1 and PO allocation, or prove that it is actually a hard problem still. Okay. Now, one has to be a little careful about when discussing the hardness of finding an EF1 and PO allocation, because from this result, we know that an EF1 and PO allocation always exists, right? So there are no instances. The only hard part is in finding such an allocation. Okay, so it's unlikely to be an NP complete problem. But what is the exact complexity of this problem for general valuations? Okay, so if people are familiar with the Nash equilibrium, the situation here is very similar. A Nash equilibrium is always guaranteed to exist, but finding one is computationally difficult in a formal sense, in the PPAD sense, right? So what is happening here? What is it easy to find EF1 and PO? Is it hard? Someone should tell me. Okay. How much of time? Say it again, Neil. Maximizing the objective, yeah. It is maximizing the objective. So checking whether there is some allocation with Nash welfare at least theta. Yes, so you frame it in the decision problem variant, yeah, because Nash is an objective, so you can do that. Whereas EF1 and PO are properties, so and they're guaranteed to exist. So it's not interesting to ask whether there exists an EF1 and PO allocation. So yeah, that's right. Exactly, exactly, exactly. And then you can do binary search over that threshold. Other questions? Okay, let's move to problem number two. Again, again a notion that we have seen already, the maximum share MMS. So remember, the maximum share was defined in terms of this thought experiment where every agent tries to partition the goods in a way to maximize its worst case utility. And I just like told you in passing that an MMS allocation is not guaranteed to exist. Uh, I don't think I gave you the reference for that. Need not exist always. This is a result by Procaccia and Wong. This is from 14. Okay, so an exact MMS allocation may not always exist, but is there an approximate MMS allocation for some approximation that is guaranteed to exist? Okay. The question is, what is the best approx MMS that is guaranteed to exist? And we know, I mean, the best answer that we know to this question is that a 3 over 4 MMS always exists. So this is a result by Goodsey et al. From in 2018. So you might have observed that these are like very, very recent results, most of them, right? Last 3-4 years, a lot of developments happening. Uh, so it is known that a 3/4 MMS, so I hope everyone remembers what approximate MMS was. Uh, the question, and we know that a 1 MMS need not always exist, but what's the right number here? What's the right threshold? We don't know that. The second question is similar to this, but about computation. Okay. So what is the best approximate MMS that we can compute in polynomial time? Like we can guarantee to output that approximate MMS guarantee. So what is the best approximation to MMS that can be computed in polytime? And the answer is actually very similar by the same paper. This is 3 over 4 minus epsilon MMS. So epsilon is any constant. A 3 over 4 minus epsilon MMS can be computed in polynomial time. And this is in the same paper by Goetz et al. But again, we don't know if this is the best. Okay. And the third question in this, in the point number 2, is similar questions, but for approximate MMS and Pareto optimality together. Okay. So what's the best approx MMS plus PO allocation that exists, and what's the best approx MMS plus PO that we can compute in polynomial terms? All right. So now for the final open question of the day. So for this, to explain the question here, I have to define a new fairness notion for indivisible goods, and that is known as EFX. It stands for NV freeness up to the least positively valued good. Sorry about the long name. So we remember EF1, right? NV freeness up to one good always exists. Great algorithms for computing it. This is very much like EF1, but stronger. So an allocation A satisfies EFX if for every pair of agents. So remember, for EF1, the definition was that for every pair of agents, there exists some good in AJ that could be removed to kill the NV. So there was, after this, I would usually follow it with a there exists. For EFX, I'm going to follow it with for all. Okay. So for any pair of agents, and for any good G in AJ, such that I values that good positively. Okay, it should not be a zero valued good, it should be a positively valued good strictly. For any positively valued good that you could remove from AJ, the NV should vanish upon its removal. The definition makes sense. So EF1 required the removal of some good from the bundle of other agent. In particular, it could be so if you are agent I, that good could be the one that you value the most. That way you take the maximum value away from it, and you have the best chance of eliminating the NV. EFX is not giving you that freedom. It's saying that for every good that you value positively, removing it should take the NV away. Okay. So I hope it's obvious that EFX implies EF1. Okay. In particular, the implications are EF implies EFX implies EF1. It's like a sandwich property. between the other two that we have seen. Okay, so this notion, I should mention, was defined by Krajanis et al. From 16. It's the same paper as the Nash welfare, the one that defined Nash welfare. The question is very simple. Okay, we know that EF1 always exists, and we discussed that EF may not always exist. But what about the sandwich property? This is a very interesting open question and has been pointed out in at least 5 or 6 papers that I know of. So a great problem to think about. Okay, so there's a few other directions, such as when agents are strategic. So far I've assumed that when you ask somebody a question, they tell you their preference truthfully, but the world is not so nice. People might try to game the algorithms, and what happens when you have strategic agents? What kind of fairness guarantees can you give in equilibrium? Okay, so again, those things are relatively less studied, unfortunately. So I think there are few papers on those, but still, I think there's a lot of work to be done on that side. So that's one thing that you could pursue. Uh, Another direction is working with the connectedness constraint, but in the indivisible world. Okay. So far we have assumed that the M goods, they are just willy-nilly. You can divide them any which way you want. Any of the good can go to any of the agents, subject to fairness constraints. But now imagine that the goods are the vertices of a graph. Okay, and you have to partition the goods in a way that the allocation of any agent is a connected subgraph. Okay, so not all allocations that were previously possible are now possible. Okay, many of the allocations might become infeasible. So there's a new feasibility constraint in the problem. Now, can you revisit all those guarantees that we had, EF1, MMS, whatever, right? So there's a paper, recent paper from Ijkai last year, I think, that came up with this problem. It has some results, but those are mostly hardness results. So it would be great to think about approximation algorithms and relaxations of various definitions. Uh, and so on. And there are many other open questions, so you should find me in the corridor sometime and ask me.